Okay, we'll start today. Good morning to you all. So we are going to start today a new topic, and this topic is known as vacuum technology, fundamentals and applications. Okay. So what are we going to see in this particular topic is the following. First, we'll introduce what is vacuum and why it is required. We'll discuss about the historical perspectives in the area of vacuum technology. Then we classify the vacuum levels. There are different vacuum levels. You can call them as rough vacuum, high vacuum, and ultra high vacuum. And we come across various definitions: pressure, pumping speed, throughput, conductance, leak rate, etc. These are various terms which we come across in vacuum technology. We will discuss about these terms. Okay. Then we will move on to how does one produce low pressures? How do you get vacuum? So for getting the vacuum, you have different types of pumps. The pumps are, for example, diaphragm pump, rotary pump, diffusion pump, oil vapor diffusion pump, then turbomolecular pump, then cryo pumps, etc. And in the area of cryo pumps, IAC has done some amount of work in characterizing the activated carbons which are used for the cryo pumps. So I will discuss some briefly about that. Then also we'll talk about an ultra high vacuum pump, or in other words, ion pump. So this essentially will tell you how do you produce these low pressures. Okay. Next, we will talk about how to measure low pressures. Okay, for measurement of pressures, you have some gauges. The gauges are Pirani gauges or thermocouple gauges. Both are different, of course. Then penning gauges and then ion gauges. These are the type of gauges which one normally uses for measurement of vacuum. Next, we should tell you how to maintain the vacuum. Suppose you have a cryogenic container and then you have to have the interspace evacuated. That vacuum has to be maintained. How do you maintain the vacuum? So we come across the materials which you have to go into the vacuum vessel, what sort of materials have to be chosen. And then there are a number of terms like degassing, outgassing, adsorption, desorption, etc. These terms we'll try to define. Then to destroy the vacuum, normally you have leaks. That means the gas, which is the atmospheric air, which is outside, we gradually enter through the leaks and go into the vacuum vessel. So what are the different types of leaks that are present? And then how does one detect the leak? Okay, there are basically two methods. One is the helium mass spectrometer leak detector, which is called helium MSLD. And then residual gas analyzer, which is also one of the techniques for measurement of leak rates, if it is tuned to a particular mass number. Lastly, we would like to conclude by talking about the applications of vacuum technology. You come across common applications like, for example, vacuum can be used to lift an object. Okay, you can take an object and lift it up by using vacuum technology. Then you come across our standard at home, we use vacuum cleaner. Okay, that is one of the important applications for vacuum. Then it is used in semiconductor industry, then thin film coating, sputtering process. Under the sputtering, I would also like to tell you how exactly we have used this sputtering process to develop zirconium nitride based sensors, temperature sensors in our laboratory under a BRNS project. Then vacuum is needed for fusion, then high energy physics. And of course, in cryogenics, you need vacuum. Without vacuum, cryogenics cannot exist. And similarly, Vacuum technology does not exist without cryogenics for getting high clean vacuum. So we'll conclude this particular topic at the end of this lecture. Okay. Okay, let us see what is vacuum. How do you define vacuum? Vacuum actually refers to a space devoid of matter. There is no matter there. So you call it as vacuum. An empty space, that is called vacuum. Okay. Now it arises from the Latin adjective vacus. It means vacant or void, empty. Okay. That's your vacuum. Vacuum therefore refers to a space where the gas pressure is less than the atmospheric pressure. Normally, you have atmospheric pressure. Atmospheric pressure is 760 torr or 760 millimeters of mercury. Okay. Now, any level of pressure below this 1 atmosphere, you call it as vacuum. Okay. Above this, you call it as pressure. Below this, you call it as vacuum. Okay. Now, as you know, 1 atmosphere is 760 millimeters of mercury. 1 millimeter of mercury is called 1 torr. So 760 torr, which is equal to 1.01325 bar. Okay. Now, 1 bar is nothing but 750 millimeters of mercury or 750 torr. Okay. Or it's also equivalent to 10 to the power 5 Pascal. You know what is Pascal? Pascal is Newton per meter square. 1 Newton per meter square is Pascal. Okay. So 10 to the power 5 Pascal is 1 bar. You can also write in terms of millibar. That is 1000 millibar is 1 bar, right? So, and the relation between 1 millibar and torr is like this. 1 millibar is approximately 0.75 torr. Okay. Or in other words, 1 torr is equal to 1.33 millibar. Okay. Why do we need vacuum? Vacuum is needed to keep the surface free of contaminants. Okay. So, for example, in this picture, you see 3 figures. The first figure is having large number of dots in a circle. Second one, relatively less number of dots. The third one, only 3 dots. Okay. Now, if you imagine that this circle is actually a chamber in which the dots are equivalent to molecules, then the first one contains large number of molecules. Okay, the second one is having relatively less number of molecules, and the third one is having very less number of molecules, or you can call it as high vacuum. So the first one can be talked about as atmospheric pressure, and then the last one is the high vacuum zone. Normally, the molecules generally move in a straight line. Okay, they keep moving from one location to another. And then when you have, for example, very large number of molecules, what do you expect? The collisions will be more between the molecules. That is, each molecule will collide to the next molecule, and that molecule collide to the third one, and so on. Okay. But when you have very less number of molecules, the number of collisions that will take place will be very less. And also, it will be molecules will colliding more with the walls rather than the molecules themselves. Okay. So we can define a parameter called mean free path. What is mean free path? Mean free path refers to the distance, average distance a molecule moves between 2 collisions. Suppose I collide here, I collide here, then you keep on counting how much is the average distance that the molecule moves between the collisions. You call that as mean free path. Okay. Now, if I take a surface, you see here I have a surface, and then if I have very large number of molecules on the surface, you see the surface is contaminated with the large number of molecules. It can be, for example, let's say a surface, let's say a clean metallic plate on which water is there. Okay, so water is a contaminant of the surface of a plate. Okay, for example, if it is a steel plate and water is there, then corrosion will occur. On the other hand, if less number of molecules are present, for example, then it is a very clean surface. Okay. So you have a clean surface or you have a dirty surface or a contaminated surface. So what do you imply is the contaminated surface contains large number of molecules, whereas a clean surface contains very less number of molecules on itself. Okay. We get an idea of mean free path for molecules is approximately equal to 1 meter distance in a pressure of 7 into 10 to the power minus 5 millibar. Suppose you take atmospheric in a chamber and then you keep on measuring. Let's say you keep on evacuating and then you bring down to the pressure levels to 7 into 10 to the power minus 5 millibar. Then the mean free path is approximately equal to 1 meter. Okay, right. Let's look at the historical developments in the area of vacuum. The Greek philosopher Democritus, he proposed that the world was made up of tiny particles. He called it as atoms, or in other words, atomos. That's a Greek word, which means undividable. That means they thought that these atoms cannot be divided further. Okay, then if there are atoms, what about the empty space between the atoms? That is vacuum. So what they thought was the empty space between the atoms, you can call them as vacuum, and that should follow all the laws of mechanics. Okay, like, atoms follow the laws of mechanics. It's also, the vacuum also should follow the laws of mechanics. He was considered to the inventor of vacuum concept. That is Democritus. He was considered as the inventor of vacuum concept. And later in Aristotle, he denied the existence of vacuum because the vacuum somehow did not fit into the basic elements of nature, namely water, earth, air, fire, etc. It could not fit into this. So he said there is no such thing called vacuum. Okay. And later in Galileo Galilei, he proved that air has both weight and density, which means I can remove air from a given space and therefore I can gradually bring down the pressure. Okay, this was in 1613, but almost in somewhere around the area in the time period from 1608 to 1647, Torricelli, he first showed that vacuum exists. What he did was he filled a glass tube of approximately 1 meter length with mercury, and the open end was submerged into a mercury reservoir or mercury pool. Then the mercury sank down to 76 centimeters from the reservoir level. Okay, so you had a height of mercury column of 76 centimeters. Okay, so the space which is left in the glass tube above the mercury is in fact vacuum. Why? Because mercury has an extremely low vapor pressure, and therefore mercury on the top of this level is vapor pressure is so small, so you have an empty space above that. That is in the glass tube, closed end of the glass tube. What was found was the mercury level was independent of the volume above. That is, you can have any amount of volume, but then this will be 76 centimeters only. Now, this was the very first successful attempt, as we see historically, which is to produce vacuum. Okay, this is the Torricelli's experiment. This was the very successful attempt to produce this vacuum. And Thomas Alva Edison, later on in 1879, he used vacuum to produce the first lamps, where a pressure of 1 into 10 raised to minus 3 millibar was used. Okay. So he had prepared the lamps, and in the lamp, actually, vacuum was used. Now you see how the vacuum level modified with years is shown here. For example, you can see the atmospheric pressure and then gradually the pressure going down in the y-axis, and the years on the x-axis. You can see somewhere around about 1700s or 1800, roughly around that 1850s, you can see mechanical piston pumps have been there, and then liquid piston pumps. Then vacuum gauges have been a lot of developments over there over the years. And you could really see that over the years up to 1900, people were already able to reach a pressure of 10 raised to minus 6 torr. Okay, there are many scientists who are involved. Boyle, Hawksby, and then Giesler, Crookes, Edison, Floyd, Colbaum, etc. Various scientists have been involved in developing the vacuum technology. Okay. Now let's consider a barometer. What's a barometer? Barometer is nothing but a device to measure atmospheric pressure. So you can see here a pool of mercury and then an inverted glass tube about approximately 1 meter in length. And then when it is inverted inside, you see there is 760 millimeters of mercury. You can see what mercury column height. Okay, this is actually the atmospheric pressure. So 1 atmosphere, this value will be at sea level. Please understand, this is at sea level at NTP conditions, normal temperature and pressure conditions. This is the value 760 millimeters of mercury or 760 tar. In terms of inches, it is 29.9 inches of mercury column, right? Okay. But if I change the pressure, atmospheric pressure, for example, if I come to a city where the sea level is the very high, all mountainous region, then where the height is much higher than the sea level, then you find the pressure is going down because the atmospheric pressure will be decreasing on elevated zones, right? Okay. Suppose instead of mercury, we use water as a manometer based on water, then barometer is based on water, then what you find is that water is less dense compared to mercury, and mercury is 13.58 times heavier, or so therefore, water column will be approximately about 10 meters in height, 10.3 meters in height, water column. Okay. So you can see here the water barometer. The water barometer height will be approximately 10.3 meters nearly, right? Okay. How do you classify vacuum? Vacuum can be classified. So first I told you vacuum refers to anything below atmospheric pressure. Okay. That is, atmospheric pressure is say 1 bar or 1 atmosphere, which is 760 millimeters of mercury. Anything below this, you call it as vacuum. So you can have different levels of vacuum. Low vacuum, 3 orders of magnitude, some 10 to the power 3 to 10 to the power 0. 10 to the power 0 is nothing but 1. Okay. So to that pressure level, you call it as low vacuum. Then medium vacuum will be up to 10 raised to minus 3 torr. Okay, 1 to 10 raised to minus 3 torr will be medium vacuum. 10 raised to minus 3 to approximately 10 raised to minus 6 torr will be high vacuum. Then you have very high vacuum up to minus 9. Then you have ultra high vacuum beyond that. Okay. So you see here, if you look at in an atmosphere, you find rarefied gases pressures are of the order of 10 raised to minus 3 millibar. The best mechanical pump can give you a pressure of 10 raised to minus 5 10 raised to minus 5 torr, and atmospheric pressure on moon is 10 to the power minus 11 torr. And lab level people can get the best vacuum of the order of 10 to the power minus 12 and slightly lower than that. And when you look at the interstellar space, that means the space between, let us say, the galaxies, etc., then you have vacuum level of 10 raised to minus 17 torr. Okay. So you can see here the vacuum scale is low vacuum, medium vacuum, high vacuum, ultra high vacuum. So very high vacuum is and ultra high vacuum are a sort of combined together. So you can say low vacuum, medium vacuum, high vacuum, ultra high vacuum. That's what the way in which it is described. And each one of them is 3 orders of magnitude lower. Okay. If I take a standard atmospheric pressure, normally, you know, gauge pressure and atmospheric pressure we have seen. For 1 atmospheric pressure will be equal to 0 in terms of gauge pressure. And 1 atmospheric pressure is 14.7 psi, pounds per square inch, equivalent of 29.9 inches of mercury. 760 millimeters of mercury or 760 torr, or you can also express in terms of Pascal, 1.01325 into 10 to the power 5 pascals, 1.013 bar, or 1013 millibar. So these are the different units which are used for designating vacuum. So please understand, when I say low vacuum, high vacuum means, low vacuum means we are closer to atmosphere. High vacuum means we are farther away from atmosphere. Okay, that means less number of molecules are present when you have this. So let's look at some basic definitions. Okay, this we know. For example, pressure, 1 atmosphere is 760 torr, or 760 millimeters of mercury, or 760, that is equal to 1 bar. You call it as bar, or it is 1 into 10 to the power 5 pascals. Okay, 1 pascal is 1 meter per second square. We come across terms like what is called pumping speed. What is pumping speed? Pumping speed means that you have a certain volume and you are evacuating that volume. Okay. Let's say some volume V of gas is removed. A volume of gas which is V is removed in a time T. Okay. Then V by T is called the pumping speed. So V by T, a certain volume is removed in a time T, then pumping speed is nothing but V by T. Okay, then we come across a term called throughput. What is throughput? Throughput is nothing but pressure multiplied by the pumping speed. Pressure multiplied the pumping speed. That means you can evacuate a certain volume at a given pressure. So that will tell you how many number of molecules are being thrown out. Okay. That's your pressure into volume. So Q is equal to P into S. That represents the throughput. Now I already defined mean free path. It is the average distance between the collisions. Okay. But what we have already seen also is higher the pressure, more the number of molecules. That means what will happen? More the number of molecules means the collisions will be many more, much more. So the average distance between collisions will be very small. Okay, the average distance a molecule travels between collisions will be very small. On the other hand, suppose I remove the number of molecules, gradually make it, dilute less number of molecules, then the average distance between the molecules keep on increasing. So obviously, lower the pressure, higher is the lambda, and higher is the pressure, lower is lambda, which means lambda into P is a constant. That is, mean free path multiplied by the pressure is a constant. So the product of mean free path multiplied by the pressure is normally a constant. Okay. There is something called outgassing. See, suppose I have a surface. On the surface, the molecules are always embedded on the surface. They are all sitting on the surface. For example, suppose I have a, let's say, a cup with water. What happens? The water normally evaporates, it goes out. But still, at the end of the entire evaporation also, still some amount of water molecules are sticking to the surface. Now, suppose I heat, then what will happen? This water molecules will try to come out. Okay. So the gas evolved from a chamber wall in units of millibar. Okay. It is gas evolved from a chamber, is you call it as outgassing rate. Okay, it's outgassing rate. Okay. Now the process of removing the gas molecules, you call it a degassing. So how do you degas? Degas means, suppose I want to pull out more number of molecules from the surface. What I do is I pump on the surface. When I pump on the surface, then more number of molecules are coming out of from the surface. Okay, that I will be able to remove it. So outgassing is a natural process of gas evolution from the chamber walls. And so what will be the units for that? It is nothing but it is happening at a particular pressure and it is happening at a particular certain volume. So therefore, the units will be nothing but millibar, referring to the pressure, into liters per second, because rate, we are talking about rate. So millibar liter per second. Okay, that is actually what you call the outgassing rate. So also the same units will be there for degassing. And then what about leak rate? Leak rate also has exactly the same units, because leak rate now refers to a gas passing through a leak into the system. So you can imagine a gas is coming in at a particular pressure into a certain volume. So gas is now getting accumulated into the vessel now, right? So it's exactly the same units are there. Okay, what about conductance? Now you remember our electrical conductivity. Please remember the electrical conductivity. Okay, what is the opposite of electrical conductivity? Electrical resistance. Conductivity and resistance are opposite to each other. Okay, in the electrical analogy, you have a potential difference. Okay, and you have a potential difference. Now there is a certain amount of resistance and a current is able to flow through this. Now the current flow is equal to the potential difference divided by the resistance, right? Now we can do it the other way. Now we call it the other way. Suppose instead of say, so we can write resistance is equal to voltage potential difference divided by the current. Okay. It is the potential difference divided by the current. What about the conductance? Conductance will be exactly the opposite. Conductance will be equal to opposite of resistance. Conductance will be just upside down. So resistance divided by the current flow. Okay, it's opposite, just opposite of that. Okay, so now we have written resistance is equal to voltage potential difference by the current. Now, if I want to write the conductance instead of 1 by resistance, if I write, it is nothing but the conductance divided by, it is the conductance divided by the potential difference, ulta, just reverse of it. Now, exactly in the same manner, here, we have here analogous situation in the gas flow. Now, the throughput is equivalent to current. What is throughput? Throughput is the gas flow. Okay. Throughput is the gas flow. It is equivalent to the electron current flow. See, imagine the atom's movement is equivalent to some electron current. So therefore, throughput is similar to current. Pressure difference is equal to voltage difference. Okay, pressure difference is similar to voltage difference. So conductance is nothing but 1 by the resistance. So if you use this analogy, exactly the electrical resistivity, electrical resistance, and the resistance to the flow of gases will be very similar. So similarly, 1 by resistance, electrical resistance is equivalent to the conductance in the gas flow system, right? Okay. I mean, if you want to know more about this, you have to go through vacuum textbooks and you will get more information regarding the conductance and so on. Okay, let's come to the flow regimes. What are the flow regimes which normally one encounters? Flow regimes means flow regions. Okay, what are the different type of flows which one normally come across? One is called the viscous flow. Now you can imagine the concept of viscosity. A castor oil is a viscous fluid. What is viscosity means? That there is so many number of molecules, one rubbing over the other and so on. So it is a viscous flow. Okay, viscous flow. Then you have got molecular flow, which means the distance between the molecules are very large. So, and then the transition zone. Transition zone is in between the viscous flow and the molecular flow. So in a viscous flow, the distance between the molecules are very small. The collisions are large, that each molecule collides with the neighboring molecule and so on. So the flow is actually directed by the momentum. That means each molecule hits the other fellow, that fellow hits the next one, that fellow hits the next one and so on. Okay. So the flow is actually dominated by the momentum transfer. And this happens at pressure levels greater than 0.1 millibar. Okay, what about molecular flow? Molecular flow occurs where you have less number of molecules, first of all. Free. Each molecule movement is almost independent. Okay, distance between the molecule is very large. So in other words, mean free path is very large. The collisions between the walls rather dominate. Okay, not the molecules, but the collision between the walls really dominate. So actually molecules flow because of random motion, not because of momentum transfer. No. Okay. Now this normally happens at pressure levels of the order of 1 into 10 raised to minus 3 millibar. Okay. And anything in between the viscous flow region and the molecular flow region is called the transition region. So now please remember this. So you have viscous flow, larger number of molecules. Then you have molecular flow, very less number of molecules. Then you have transition region in between. Okay. Now you see, you can see the picture of viscous flow and molecular flow here. So you can see here a very large number of molecules here in the viscous flow and the very less number of molecules in the molecular flow, right? Okay. So obviously, when I said viscous flow and molecular flow, viscous flow means mean free path is very small and molecular flow means mean free path is very large. So now, how do you define? So suppose I have a container, then you can think of some distance between the walls of the container. So mean free path divided by the wall of the container, the distance between the walls of the container, you can call that as characteristic dimension. Okay. This value is less than 0.01, then you call it as viscous flow. Okay. Mean free path divided by the characteristic dimension is less than 0.01, you call it as viscous flow. And when it is greater than 1, you call it as, the molecular flow. Anything in between 0.1 and 0.01, you call it as a transition flow or transition region. Okay. Just to get you an idea of the number of molecules that are present, okay, in a vacuum system, in a system, for a molecular density and mean free path, what sort of distances we are talking about. But just to get an idea, let's start with atmospheric pressure. If you take 1 atmospheric pressure, how many number of molecules are present? Okay, the number of molecules present in 1 cc of gas is approximately 30 million trillion. That is 30 million trillion gas molecules are present in such a place. Okay, very large number of molecules. Okay, now suppose I reduce the pressure by 6 orders of magnitude. So I am going to 1 into 10 raised to minus 3 millibar. So in such a case, the number of molecules that will be present is 40 trillion. Okay, we are coming down in the number of molecules. Okay, I go another 6 orders of magnitude down. So I go to 1 into 10 raised to minus 9 millibar. I mean, I'm going to ultra high vacuum zone. Then the number of molecules are 40 million. Even then the molecules are not less. It is 40 million molecules are present. Okay, what about the mean free path? The mean free path, for example, in atmospheric pressure condition is about 6.4 and 10 raised to minus 5 millimeters. Such a small distance between collisions, right? So the mean free path is so small. Okay. Now, if you come to 10 raised to minus 3 millibar, then it's about approximately 5 centimeters. And when you go to minus 9 millibar, it is 50 kilometers. Please understand, mean free path is 50 kilometers. So that is the large distance between the collisions, average distance between the collisions. Okay. So far, what we have seen is, we have seen what is vacuum, what exactly what is the meaning of mean free path. We discuss also some definitions of pumping speed, throughput, all those things we have discussed now. Now, we have seen the different levels of vacuum. That is, you have what is called the low vacuum, medium vacuum, high vacuum, ultra high vacuum, etc. That's these things we have seen. Now what we'll see is how to produce this vacuum. How exactly one can produce this vacuum. Right? So, I mean, don't worry about this table. This table gives you almost all sorts of pumps that are available to produce vacuum. Basically, one can think of, so if you start with the vacuum pumping, there are basically 2 methods to produce vacuum. One is, I can take the gas molecules and throw it outside. Okay. That is what is called gas transfer pump, vacuum pump. That means I'm taking the gas molecules, throwing it outside. So you can call it as gas transfer pump. On the other hand, I can also do another thing. Suppose if there is a vacuum space, some vacuum, some zone where you have to evacuate, I take the molecules and then put them in an enclosure. That is, it's not visible to the surroundings. I am putting it in an enclosure, or in other words, making it entrapment. Okay, the gas molecules are trapped in some location such that it's not available for heat transfer or any other methodology. Okay, so two methods are there: gas transfer and then entrap. Now, coming to the gas transfer, there are many methods. One is the positive displacement type of pump, and then kinetic pump. In the positive displacement, the gas is drawn, pulled, thrown out. Again, drawn, pulled, compressed, thrown out. Drawn, compressed, thrown. That you call it as positive displacement vacuum pump. In the kinetic pump, the gas molecules are gradually pulled out, and then thrown out. Okay, that is your kinetic pump. Okay, so there are pumps like reciprocating displacement, rotary pump, etc. fall under the category of positive displacement pump. Your what shall I say, diffusion pump, turbo pump, okay, and then gas jet pump, liquid jet pump, etc. They form the kinetic pump. In the entrapment pump, you normally have adsorption pump, cold traps, getter pump, sublimation pump, etc., or cryo pump. All these things fall under the category of entrapment. So now you see the vacuum can be produced in two ways, either by removing physically all the molecules and thrown out, or you can collect all the molecules and put them securely one place. Okay, that is what is called entrapment. Now let's start with the basic rough vacuum pumping system. Okay, now coming to the operating ranges, as I mentioned, rough vacuum, high vacuum, ultra high vacuum. We categorize in this manner. So here is your atmospheric pressure, and then you have 10 to the power 2 torr, 1, and then somewhere 10 raised to minus 3 torr. Okay. So from atmospheric pressure to 10 raised to minus 3 torr, you call it as rough vacuum, right? This is the level. Okay. So what are the pumps which are there in this zone? One is rotary vane mechanical pump, then rotary piston mechanical pump, dry mechanical pumps, and then you have roots blower or booster pumps. So these are the pumps which are useful in this range, right? Okay. Now, I will talk about the rotary pump. What is rotary pump? Rotary pump is, you can see a picture of the rotary pump here. This can be a single stage or two stage type of pump. Now, what exactly the rotary pump is doing is the following. So here outside is the space which has to be evacuated, right? This is the zone where you want to evacuate. So what it done is it has two parts. One part is, see, one roller is rotating within another housing. Then you have actually a vane. This is the vane. This is the vane, which is spring-loaded vane. So that vane, depending, it's an eccentrically, the roller which is rotating is located eccentrically with respect to the housing. So the vane will extend or it will compress, extend or compress, like that it will keep on happening. So what happens is the gas is now drawn inside when it is in this position. Then the gas comes through this. By the time when it rotates, the vane comes to the other side. Now the gas is compressed in this zone. So you can see the volume keeps on decreasing. So it is getting compressed. And you can see when it is compressed, you can see the color becoming darker. And then the compressed gas is thrown out outside. So the gas is drawn from this opening, and then it is taken in small quantity, it gets compressed and then thrown out. Okay, how does the vane seal? The rotary vane, the vane which is there is a spring-loaded vane. How does it seal? For sealing, you use oil. So what is normally done is you use oil for sealing. So the gas is drawn, okay, and then it is in a sealed with oil. So you have an oil in the rotary pump. So the gas is trapped and goes into the other side, and then it is compressed and it is pushed outside. Okay. So this is what is called rotary vane oil sealed pump. Okay. Now you can have single stage, you can have multiple stages, etc. You can have, that means single stage means in one stage, there is only one rotor and then one of them is there within housing. Two stage means the first stage output is given to the second stage input and so on. So that's a two-stage system. You can also do the same process in a different way by using what are called scrolls. Scrolls are nothing but helix, which are, multiple helices. So you can see here, you can see here two helices. One is somewhat brown in color. Another one is somewhat red in color. So this helix is what they have is one helix moves within the other helix in an eccentric manner. Okay, in eccentric motion. Okay, what happens during the eccentric motion is the gas is drawn, gradually compressed, and then it is pushed out to the outer end. Okay. So in the scroll pump, this is called scroll pump. This scroll pump, normally you do not use oil. There is no need for sealing. Oil is not used, but use a material such as Teflon, etc. For the preparation of the scroll. Okay. And it has, the scroll pump has high pump. That means one of them is stationary, another one is the rotating continuously. Okay. The process of rotation makes sure that the gas is drawn from one end and then thrown out to the other end. Say, for example, it is drawn from, let us say, the periphery, okay, and then gradually entered to the center and thrown out. Okay. So you have this, normally a scroll pump has high pumping speed. It is quite compact in size, and normally the base pressure is of the order of some millitorr, etc. You will have the base pressure. So this is the commercial unit, what you see here, the scroll. Okay. Now let's come to dry vacuum pumping system. Okay. What do you mean by dry vacuum pumping system? That means there is no oil in this dry vacuum pumping system. The dry vacuum pumping system, you can call them as one type of pumping is called diaphragm pump. What is a diaphragm pump? The diaphragm pump contains a diaphragm. This diaphragm is made to move up and down like this. The diaphragm will be moving up and down. How it will move up and down? It's because it is connected to a shaft, a motor shaft, and the shaft, as it rotates, this will move the diaphragm up and down. Okay, it has two sets of valves, one set of valve for the inlet port, another set of valve for the outlet port. So when the diaphragm goes downwards, the inlet port opens, it takes the gas inside. And when the diaphragm moves upwards, the inlet port is closed, the outlet port is open, and the valve is open and the gas goes up. So each time it will draw the gas from the inlet port and then throw it at the outlet port. Inlet port gas is drawn and then it is thrown out at the outlet port. So this oscillation of the diaphragm alternately pulls the gas from one port and then expels it to the other port. So normally these pumps are quite clean, because what about the diaphragm material? The diaphragm materials can be rubber, okay, or any suitable material which can withstand a lot of fatigue. Okay. But normally these oil-free pumps are clean, but somewhat slower in operation and also more expensive because they are free from oil. Okay. But many times they are quite useful to use oil-free diaphragm pumps. Okay. You can see here the diaphragm pump, two-stage diaphragm pump, this one. Okay. And you can also have diaphragm pump in this manner, where you have an eccentric cam. As it moves forward and backward, the eccentric cam makes sure that the piston moves upwards and downwards. And each time one inlet valve opens and then an exhaust valve is, after the gas is trapped, the exhaust valve opens at the other time. other location. Okay. So this is an alternate way of doing the diaphragm pump also. There are also other type of pumps called blower pump or booster pump. Okay. What is the booster pump? The booster has two lobes. Okay. There is one lobe, there is another lobe. The lobes are arranged such that they are sealed in between. Okay. So you can see here the inlet, gas is drawn. The two lobes are rotating such that gradually it slides over the other. You can see the different positions, A, B, and then C, and then D. So the gradually as it keeps on rotating, a certain amount of gas is trapped, and then it is moved by the end of the rotation to the other side. Like that, it keeps on going. Okay. So inlet to the outlet, it keeps on moving like this. Now, a big size roots blower pump. Normally, this roots blower pump or blower pump or booster pump does not produce very high vacuum levels, but they are able to pull out large quantity of gas and throw it outside. Okay. So they are very good in that. And usually for pumping on helium gas and so on, suppose I want to pump on liquid helium, then these type of pumps are generally used. Okay. So the booster pump again does not use any oil. So it is again a dry pump, what we are talking about. Okay. So diaphragm pumps are dry pumps. Okay. There is another class of pumps which are called screw pumps. The screw pumps are, there are two screws. One screw interlinked with another screw, and one is a stationary screw, another is a rotating screw. As the screw is continuously rotating, then what happens is the gas is drawn and then gradually compressed and then thrown outside. Okay, so it keeps on evacuating. So you can see here the operation of the screw pump operation as you keep moving from one end to the other. The gas is drawn, gradually compressed, and then it is thrown outside. So by this process, you get the evacuation. Okay, normally the pressure of screw pumps, etc., are somewhere about 1 into 10 raised to minus 1 millibar to about 5 into 10 raised to minus 2 millibar. This is the sort of range which it operates. And the pumping speeds are somewhere about 90 to 460 cubic foot per minute. That's as a screw pump. Okay, how does the pumping speed vary as a function of pressure? You can see here at high pressures, it has a fairly high pumping speed. And as you keep on reducing the pressure, the pumping speed goes down. And then at somewhere around 10 raised to minus 3 torque or millibar, the pumping speed is practically zero. So this is the type of pumping speed what you get. Okay, let's come to high vacuum pumps. In the high vacuum pumps, you use the range is from 10 raised to minus 3 millibar to almost about 10 raised to minus 8 millibar. Okay, this is the high vacuum pump. So what are the pumps that are available for this? Here you have diffusion pump, and then a turbomolecular pump, and then you have a cryo pump, and generally you can also use liquid nitrogen traps as pump, and then ion pumps. Okay, so these are the various type of pumps that can be useful for high vacuum, producing high vacuum, right? So let's start with the vapor jet diffusion pump. So you can see the vapor jet diffusion pump is shown here. Okay, this is the inlet and this portion is the outlet. Okay, how does it work? So what it has is at the base, it has high molecular weight oil, Okay. Okay. So this high molecular weight oil is heated, okay, by a heater at the base. So when you heat the high molecular weight oil at the base, then the oil vapors gradually move upwards. It goes upwards, and then there are larger number of jets, as you can see here. These are the jets, and then the gas moves. There are multiple jets are present. The topmost jet, and then the second level, third level, etc. Multiple jets are there, and the oil vapor now flows downwards like a jet at very high speeds. Okay, vapor molecules are now going downwards, at highly accelerated speeds. During the process, it pulls all the molecules which are gas, which are just at the top. So whatever gas molecules which are at the top of this diffusion pump, they are all gradually pulled downwards and then they come downwards here. You can also see a set of pipes which are wound over the diffusion pump, and these pipes carry cold water. So as the jets move downwards, then the oil is condensed, the vapor is striking the walls, then oil is condensed, then the vapor jet becomes oil, turns out to be the oil and gets collected at the bottom. So what happens is the process continuous. So you have from the center, the oil is vaporized, it goes up, then forms a jet, and the jet is going downwards and then pulls all the gas molecules from the upper space, goes down. And as it comes down, the oil vapor molecules are all condensed and then again become liquid oil. Okay. So now it is making sure that the oils is not, so what you see is high vacuum on the upper end and then the low vacuum at the bottom end. So the molecules are now collected at the base of this pump. Okay, and they have to be removed out. So you require a backing pump. This backing pump makes sure that these molecules are continuously removed. Okay. So this is what is called vapor jet diffusion pump. So what do you use here as the oil is high molecular weight oils are used here. Okay, and you cannot expose this to atmosphere because it will get oxidized, and then the long molecular chain molecules will break into smaller pieces and the vapor pressure will continuously increase. So it gets tarnished or tarred if you expose it to, when in the heated condition, if you expose to ambient, then automatically the oil gets charred. Okay. You cannot do that. Okay. So obviously you can see for a vapor jet diffusion pump, you require a backing pump. This backing pump is needed because it will have to take out all the molecules which have come from the top end, which has reached the bottom. It has to be pulled out so that next batch of gas molecules can keep on come down. Okay. Otherwise, you will build up a pressure at the bottom, and these molecules will be again going backwards and backspin. So you must remove them out. So normally a rotary pump is used as a backing pump in such case. Okay. Next we have what is called turbo molecular pump. If I am interested to get a, let's say a very high clean vacuum, then I use what is called turbo molecular pump. What does it have? The turbo molecular pump, you can see here the structure. You have two sets of blades. One set of blade which is rotating, another set of blade which is static. Now the set of blades, one rotating, static, they are alternating each other like this. Rotation, static, like. So the static blades are all present in certain orientation. The rotating blades, actually, they are connected to a common shaft in the bottommost point, and it is a motor which is rotating. So now the gas molecules which are appearing on the top of this pump, it is they are moved by the rotating gas molecule. Then next it enters a static, then it goes to rotating frame, then static, then rotating. So ultimately the gas molecules are gradually pulled from the topmost point to the bottommost zone, where again the pressure builds up, and this gas has to be thrown out again by using additional, let's say, a rotary pump. Okay. Now, this gives you a detailed structure of the turbomolecular pump. So you can see a set of rotating vanes and then static vanes, rotating vanes and static vanes, etc. The angles are continuously varied from top to the bottom. And again, as it reaches the bottom, the gas molecules are thrown out, okay, through the opening. So as in the case of a diffusion pump, you also require a backing pump for this case. This is very similar to a jet engine alternate rotor and stator blades assemblies are arranged, and the rotor blades, they rotate at speeds of the order of 20 kilo RPM to about 90 kilo RPM, and they force out the molecules. Again, as before, it requires uh, low or medium vacuum behind, and therefore you require a pump. 4 pump is required for evacuating these molecules. What about the pumping speeds? The pumping speed essentially depends upon the molecular weight of the gas molecules. So the larger molecules are pumped more efficiently, because again, it is basically it is the sort of momentum that the veins transfer onto the molecules. So heavier molecules are evacuated better. So for example, you see here the pumping speed as a function of the pressure. So you have the nitrogen, and then helium, then hydrogen. And initially up to some, when you have low RPM, you do not have much of a pumping speed. But when you cross about 10 raised to minus 1 Pascal, you have a constant pumping speed. So helium, nitrogen is the highest, and next followed by helium, and next followed by hydrogen, because they depend upon the molecular masses of these gases. Okay. So the turbo pump, the molecular pump do not pump all the gases with the same efficiency. Larger molecules are pumped faster than the smaller molecules. Okay, this gives you a structure, a little more detailed structure. There are two sets of bearings which are used. One is called the radial bearing, magnetic bearings, and then axial magnetic bearings are used. And so that the system is quite stable. And especially since you have very high rotational speeds and with the very small clearance gaps, you require very precise alignments of these the rotor and stator blades. Okay. Now the compression ratio for various gases are plotted as a function of the 4-line pressure. Here, as you can see as before, the nitrogen has got a higher compression ratio compared to helium, which is again, then hydrogen one is the smallest in all. Okay, now we come to what are called cryopumps. I think with this cryopump, I'll just talk for a while. Okay, let's come to cryopump. Or shall we take a break now? Hello? Before we start the cryopump?
Yes, sir.
Hello?
Yes, sir.
Shall we take a break now for about 5 minutes? Okay?
Okay, sir.
Renju? We'll take a break of
Okay,
5 minutes
sir.
now and then come back. What's the time now?
11:06.
11:06. Okay. We'll be back by about say 11:12 or 11:30. We'll come back. Okay. Just take a break, small break. Uh, are you people back now? Shall we start?
Yes, sir.
Okay, shall we go ahead now? Okay, now we will discuss about cryopumps. So as you can see here, we have discussed about rotary pumps. Okay, then diaphragm pumps. Then we discussed about the diffusion pumps, then turbomolecular pumping system. Now we are going to discuss about cryopump. That is, we are gradually becoming better and better in vacuum. Okay, so now we are going to the zone of cryopumps. Okay, the name itself implies that it requires cryogenics, right? Okay, now let us look at the vapor pressure of the various substances. Okay, for example, this vapor pressure of a substance is plotted of different gases, for example, water, water vapor, carbon dioxide, nitrous oxide, oxygen, nitrogen, neon, hydrogen, helium, etc. Now you can see the vapor pressure at a given temperature, what sort of vapor pressure it will be having, each one of them will have. Okay, the x-axis is in the temperature scale in Kelvin, and the y-axis is in the vapor pressure in units of torr. Okay, and we can see here the sort of the boiling points of these various fluids. Okay, so you can see here water boils at 100 degrees centigrade. Okay, and you see the sort of vapor pressure is 1 atmospheric pressure. Okay, and now as you decrease the temperature, what happens to vapor pressure? It keeps on decreasing. Okay, and when you go down to, let us say, somewhere close to 150 Kelvin, you see the vapor pressure goes to 10 to the power minus 11. Okay, it's become very, very, very small, extremely small. So also, for example, carbon dioxide, nitrous oxide. See, as the boiling point of these fluids become lower and lower and lower, then the vapor pressure for values are slightly higher and higher. For example, if I take helium, so helium boils at 4.2 K. So at 4.2 K, the boiling point at the vapor pressure is 1 atmospheric. Okay. For example, at 77 K, where is 77 K? Yeah, 50, 70, 60, 70, 77. Yeah. For 77 K, minus 196 degrees centigrade, the nitrogen has got a boiling point of 1 atmosphere. So what we notice is that the vapor pressure of a particular gas is actually depends on its boiling point. So the vapor pressure, the lower the boiling point of the fluid, the more will be its vapor pressure at that particular temperature. Okay. So if I have the higher boiling point component will more or less be frozen at a lower temperature. Okay, this will what will happen. Okay, so we are going to make use of this effect of the variation of vapor pressure as a function of temperature for different boiling point, different materials with different boiling point. Okay, what happens? Let us try to understand what is cryocondensation. What is cryocondensation? Suppose I have a surface which is you can think of a plate. Okay, it is cooled to, let's say, liquid nitrogen temperature. Okay. Now you have gas molecules which are coming in. The gas molecules now will come onto the surface. Let's say atmospheric air molecules are coming in and then going. You can see the out inner, it contains large number of layers, 1 layer, 2 layer, 3rd layer, 4th layer, etc. Number of layers are now getting gradually accumulated over there. The very first layer at the bottommost zone is actually tied to the your material. Okay, whatever is the plate, on the plate, the first layer is more or less fixed. Okay. Now, what will be the temperature of that layer? The temperature of the layer will be the same as that of the plate. Okay. What about the next layer? The next layer will be slightly warmer. What about the next layer? The next layer will be still further warmer. So this layer will be further warmer. This layer will be further warmer. So it will keep on increasing. The layer temperature will keep on going up and up and up. And the at particular level, the layer temperature is sufficient enough such that some molecules will be coming in, some molecules will be going out. So there will be an equilibration taking place between the layers, the molecules which are entering, and then molecules which are going out. That at that particular zone. What is this process? This process is called condensation, cryocondensation. So in the cryocondensation, you have one layer which is very much tied to the base, next layer, 3rd layer, 4th layer, etc. As you keep on increasing the more and more number of layers, the temperature of this layer becomes higher, higher, higher. Like, okay. Now you can pump a gas by using the process of cryocondensation. What exactly we do? We present a plate. You imagine that you present a particular plate which is cooled to very low temperature. Then all the molecules which are surrounding that will keep on condensing on its surface. Okay. And so what about the gas pressure? If suppose you have an initially high vapor pressure for the gas which is surrounding, because of this condensation, the vapor pressure, now the pressure surrounding this goes down. That means you have got a pumping. So pumping happens due by cryocondensation. This is what is called cryocondensation pumping. So this is one method of pumping. So that means if I want to pump a gas, all I do is introduce a surface which is cooled to very low temperature. If I introduce that, automatically by condensation, the vapor pressure is continuously reduced, so you get the pumping effect, right? Okay. For example, the cold traps which are used in diffusion pump systems, they actually operate as cryocondensation pumps. So what do they have? You have here the liquid nitrogen filling in these chambers. Okay, this is an annular chamber, as you can see. And the topmost zone is the zone where you are pumping, and the bottom is actually your pump. See your diffusion pump. So the vapor molecules, gradually the vapor molecules of oil vapor molecules are going to come upwards. And because these are all connected here, okay, there is a set of plates connected here. So the molecules which are coming up onto the top are cooled to liquid nitrogen temperature. So therefore, the oil vapor molecules will now get condensed on these surfaces. On these surfaces, the molecules will now get condensed. On the surfaces which are cooled to low temperature, it will automatically get condensed. Okay. So it will form a certain layer. It will get fixed and form a certain layer. So the gas is now trapped on the surface of this. Gas is now trapped on the surface of the metallic layer, metal surfaces, which are cooled to low temperature, on the chilled surfaces. So they are called cooled traps, okay? Because by cooling, you are able to trap all the gas molecules. So they are called cold traps, right? We can also think of alternate way of pumping gas molecules. This is by what is called cryosorption. That is by the process of adsorption of the gas molecules. How do we do this? We present actually a material which has got a lot of porous surface. Suppose I have a material like activated carbon, or let us say silica gel, or let's say zeolites. These are different materials which have porous structure. Now, suppose these porous structured materials are cooled to low temperature. Then the incoming gas molecules enter into this porous structure. Say the gas molecule comes here, enters, then it goes to the next one, etc. And then get trapped inside into the internal pores. Now, this trapping can happen not necessarily at very low temperature. It can happen even at a slightly elevated temperature, because gas molecules will be entering and then they'll keep moving into the pores like this, right? Now, this process of holding the gas molecules is by what is called adsorption. By van der Waals forces, the gas molecules are now attracted to the surfaces, and therefore it is called cryoadsorption or cryosorption. So the pumping of the gas molecules takes place by the process of cryoadsorption. Okay. So now you please remember, we talked about two types of pumping. One type is positive displacement. That is, you take the gas molecule, throw it outside. That's your rotary pump or your diffusion pump, turbomolecular pump, etc. Now we have the other part where the gas molecules are trapped, entrapment process. So there are two pumps we have seen. One pump is by the cryocondensation pump. Another pump is the cryosorption. Okay. Now the sorption pump components are generally, so what exactly the sorption pump components? They are like this. Suppose I have liquid nitrogen and I want to evacuate a particular space. All that I do is this liquid nitrogen, you insert a container which has large number of panels onto which molecular sieves, or in effect also you can also use activated carbons, can be attached to the cold surfaces. So when you insert this can inside the liquid nitrogen, the outer surfaces are cooled to low temperature. Okay, so the panels are all cooled to low temperature, and ultimately, because the panels are now cooled to low temperature, okay, the gas molecules which are coming inside, they get trapped onto these cold surfaces into the molecular sieves which are cooled to low temperatures. Okay, so now you produce higher vacuum of the space what you are trying to pump. Okay. So this is the typical structure of the sorption pump. You can also have a sorption pump using cryogenic fluids. So you can also use liquid helium for or liquid nitrogen or liquid hydrogen for at different temperature level. So if you use liquid helium and activated charcoal, you can get adsorbers to pump to about 10⁻⁻12 torr pressures, and it can have very high pumping speeds. There is no vibration in this process, and also it is not dependent on the external magnetic fields. Okay, so no effect of magnetic fields as well. What needs to be done is, as the gas molecules get trapped into the cold traps, into the adsorbent, the adsorbent needs to be periodically baked or heated, and along with the rotary pump or roughing pump, these molecules are to be thrown out. Okay, so this is the process of desorption. Adsorption is the process by which gas molecules are getting into the pump. Desorption is the process where the gas molecules are thrown out of the pump. Okay. Normally, if you want to use liquid helium, then it is pretty expensive. Okay. And therefore, what people do is they use what are called cryocoolers. Okay. Or cryorefrigeration systems. Okay. And that cools helium, that cools a charcoal panel so that you can get cryosorption pumps. Now you see a typical cryosorption pump based on a cryocooler is shown here. So this part is the cryo pump. This is the second stage, and this fellow is the first stage, and this is the drive unit. So this forms a cryocooler. On the cryo stage, second stage, you have a set of panels which are attached, and they contain the activated carbons which are attached to the cryo panel. So they are activated carbons are all attached to this particular surfaces here. Okay. Now the first stage, cooling power, is made use of for as a radiation shield for the second stage. Okay. So the condensed gas, suppose whenever I doing a bake out, I want to evacuate this zone, then I use the pump out port and then evacuate it. Okay. Right. Now the commercial, there are many companies who are able to give you commercial cryopumps, and basically the commercial cryopumps will contain a cryocooler, okay, on the top of which is activated carbons are attached on the second stage. The first stage is used as a radiation shield for that. Okay, that forms a cryopump. Now, to drive the cryopump, you require a helium compressor. So that means the cryocooler can be driven by using a helium compressor along with a set of flexible hoses which are connected here. So this is the sort of arrangement what we saw little in the previous figure. The same thing is redrawn in a slightly different manner, different way. Okay. I would like to present before you a small development which was carried out at IISc. This is called the Adsorption Characterization Facility, which was built for development of cryosorption pumps. Okay. As we see, for example, activated carbons can be obtained from different sources. You can have, let's say, coconut shell charcoal, or you can have different type of charcoals like the charcoals from, let's say, flake kneaded charcoal, flake kneaded type, the commercial charcoal, the synthetic type or natural type charcoals are available. Different type of charcoals are possible to be used. In all these cases, we have normally the data at either at the room temperature or at best at liquid nitrogen temperature. The data of adsorption of gases like helium, etc., are not available at low temperature. So what is really needed is you need to know what is the characteristic of adsorption characteristic of the activated carbons at these, on these charcoals. So for doing that, IISc developed a special system using a micropore analyzer. So what we did was we purchased a micropore analyzer from Quantachrome Instruments. This is the instrument, and the characteristics of adsorption is shown here for a standard sample. Okay, this red color curve gives you the adsorption pattern, and the blue dots correspond to the desorption pattern. It plots the volume adsorbed at STP as a function of the relative pressure here. Okay. At liquid nitrogen temperature, you can try with the different type of activated carbons like carbon granules, okay, activated carbon fibers, flake knitted types, okay, then you have non-woven type activated carbon spheres, different type of activated carbons have been plotted here. So whatever the experiment, what was done was, the characterization experiment done was, we would like to know the data of adsorption at low temperature. So for this purpose, a cryocooler, GM cryocooler was used. The GM cryocooler will be able to produce a low temperature. Okay, it will be able to produce a low temperature on a small zone wherein the on the second stage, wherein the charcoal will be mounted, and then the adsorption characteristic on this charcoal will be determined by the Quantachrome instrument. So the GM cryocooler was initially characterized. This is the cool down curve. This is the heat load curve of the GM cryocooler. And of course, I don't want to go into more details on this. It's a sample chamber along with heat switch and so on. And these are the system assemblies. This is the second stage of the cooler on which sample chamber is mounted. Then the sample chamber is connected to this pipeline to the quantachrome instrument. Okay, and then it is super insulated, surrounded by radiation shield is added, and then it is evacuated, and ultimately it is the total experimental system is shown here. Okay, now the adsorber characterization is done by the quantachrome instrument, and the necessary refrigeration is produced by the GM cryocoolor system. Okay, so you are able to do an integrated system starting for characterization right from about 4.5 Kelvin to 77 K. This is the total system. And we were able to characterize different type of activated carbons like carbon granules, carbon pellets, activated carbon spheres, the spherical shape, activated carbon fibers, non-woven type or flake knitted types, etc. Different carbons were characterized. And you get the characterization at different temperature level, 4.2 K, 5 K, 10, 8 K, 10 K, etc. So this will tell you what is the performance of the activated carbon at different temperature levels. So you choose the best activated carbon for preparing your cryo panels for pumping of, especially pumping of helium. Normally, when you characterize, you get what is called the BET surface measurements are done, and you get the surface area for the measurements. And this gives you the surface area measurements at 77 K, 4.5 K, 5 K, 8 K, 10 K, etc. So you can see here the activated carbon spheres is actually one of the best charcoal that is available on this system. Okay, these were the development which are done under BRNS project. Okay, coming back again, back to the pumping systems. Now we'll discuss about the ultra-high vacuum pump systems. Now, when we talk about ultra-high vacuum pump system, we have to talk about ion pumps and sublimation pumps. These are the pumps which are useful for high vacuum to ultra-high vacuum pumping. Now, let us try to talk about the pumping of a gas by ion pumps. What does the ion pump contain? It contains a set of anodes and then a set of cathodes. Okay. The cathode is generally made out of titanium. Okay. Titanium cathodes are present at the base. Just a minute, please. Titanium cathodes are present. Now, anode is actually, anode is the one which is in the middle, as you can see here. Okay. Now, what you do is you apply a high voltage and produce free electrons. And the free electrons, when they are produced, they ionize the gas molecules. And so the background gas is now ionized by the electrons. Now, normally when you have electrons, ions together, then positive ions will be accelerated towards the cathode. The cathode is your titanium-based system here, the hatched zones here. And the atoms of titanium cathode are also emitted. Now the ions are now bombarding the titanium cathode. So therefore, these ions will now eject titanium atoms from here, and they will be emitted out by sputtering. And they go and cover, you can see the reddish color things there on the bar, on the top, on the anodes, and they go and cover the anodes. Okay. Now the molecules which are hitting the active titanium film will now get chemically trapped. Okay. Background gas molecule hitting the active titanium film will get trapped. Some of the accelerated positive ions moving towards the cathode also get buried towards the. But the so-called trapping into the cathode is not a permanent solution, because the next layer of atoms which are hitting the ions which are hitting the cathode will now remove out these molecules again. So therefore, pumping at the cathode is not permanent. So the previously pumped atoms are now released, as the sputtering process proceeds. So what happens is the net pumping speed decreases initially until you get an equilibrium condition where the number of molecules which are getting implanted are the same as the number of molecules which are being, sputtered. So what effectively happens is there is a net pumping of the gas molecules. So you are able to do by the ion pump, the pumping of the gas molecules. Okay. Now at an equilibrium condition, when this happens, then the pump is sort of saturated. So what you should do is you should now again make sure the pump is come back to the original condition by reconditioning. Okay. I talked to you about the ion pumping system. Okay, there are also getter ion pumps are there, which can be useful for producing ultra high vacuum system. I'm not discussing that in detail because of want of time. Let's talk about how to measure the pressures. Let's go back again. We start with rough vacuum, then high vacuum, then ultra high vacuum. As you can see here in the rough vacuum, you use Bourdon gauges. Then you use also the thermocouple and Pirani gauges. Then capacitance manometers are the ones which are useful for rough vacuum measurements. When you come to high vacuum, you use cold cathode gauges, hot filament gauges, okay, and then ultra high vacuum ion gauges. You can also use residual gas analyzer as one of the gauges for measurements of pressure. Okay, let's start with the Bourdon gauge. Now, the Bourdon gauge is this instrument you have seen. For example, these are nothing but the pressure gauges which are attached to your cylinders. Okay, normally it will start with the 0 level, but this Bourdon gauge, as you can see, it has also a negative scale. So it has also a negative scale starting from 0 to 30 inches of mercury or 0 to 70 centimeters, which is in the vacuum scale. Okay. What is the content? How does the Bourdon gauge inside look? What it contains is an elliptical shaped tube, okay, which is connected to the closed at this end, and this one is connected to the vacuum zone. So as you keep evacuating here, then there is a distortion of the elliptical tube. Now the distortion of the elliptical shaped tube is modified using levers and gears, you along with a needle to indicate the vacuum level. So as you can see, as you keep changing, the needle will now indicate the vacuum level. So as you keep evacuating, initially it will have 0 somewhere here and then keep on decreasing. And as you go on improving the vacuum level, it keeps on going downwards. Now, the gauge which contains both the positive and negative indications, this is what is called a compound gauge. Okay, these are normally used by refrigeration specialists because normally you may have to evacuate and then you have to also fill pressure. So you have a gauge containing both the positive side and negative side with respect to atmosphere. That is called the compound gauge. Okay. Let's go to the heat transfer gauges. In the we are now trying to measure the vacuum level up to 10⁻³ millibar. This is done by either the thermocouple gauge or also Pirani gauges. Both gauges are used. So what is the thermocouple gauge? Its gauge will look like this. What is the content of the thermocouple gauge? It has a filament, and the temperature of the filament is measured by a thermocouple. So it is based on heat transfer. So you normally measure the temperature of the filament, okay, in the presence of the gas. As the gas molecule, more number of molecules are present, then the temperature of the filament will be low. When the less number of molecules are present, that means as the system gets evacuated, then the temperature of the filament will go up, obviously. So you monitor the temperature of the filament and equate it to that of the pressure, and that is what is called a thermocouple gauge. On the other hand, you can also monitor the resistance of the filament and and in relation to that of the pressure, if you measure the resistance of the filament, heated filament, then as a function of pressure, then that will indicate what is called the Pirani type of transducer. Okay. So the more the number of molecules, the less will be the resistance, higher will be the lower will be the temperature, and this less number of molecules, more will be the temperature and more will be the resistance. Okay. So that is what is called the Pirani transducer or Pirani gauge. You can also measure pressure up to 10⁻⁻5 torr using what is called a capacitance manometer, which consists of two metallic plates separated by a diaphragm, so which forms the capacitor in between. So all that you do is, one side is evacuated, the other side is having a reference pressure. So you can now monitor the movement of the diaphragm will tell you, it will change the capacitance of this gauge. And by this monitoring this, you will be able to measure the pressure of the space. You calibrate the capacitance as a function of the pressure. So which is called capacitance manometer. Okay. Now we are now talking about what are called cold cathode gauges or penning gauge. What is a cold cathode gauge? The cold cathode gauge has got a filament. It is not having a hot filament. The electrons are not created by the hot filament, but just by the high voltage discharge. So it has a cold cathode will have a 2 kilovolts voltage across, and there'll be the electrons are now generated. Now, this in the presence of the magnetic field, the electrons will now collide with the gas molecules. And when they collide with the gas molecule, they produce ions. The magnetic field is able to contain these ions as an electron plasma, and it will try to ionize the rest of the gas molecules. And now the amount of current that it produces is directly a measure of the directly a measure of the pressure of the system. Normally, a pressure in the range from about 1 into 10⁻⁻2 millibar to 10⁻⁻9 millibar, one can measure using the penning gauge. Normally the measurements at high pressure in an ion gauge often is less reliable than an ion gauge in the case of a penning gauge. And because it is also because the ion current is not proportional to the gas pressure, and therefore a cold cathode gauge or what you call penning gauge cannot measure very accurately very low pressure ranges or very high pressure ranges. Okay. Now we'll talk about what is called ion gauge. What is an ion gauge? Ion gauge has a filament, as you can see the structure here. It has got a filament, okay, which is used for emitting the electrons. And normally it contains a collector, and then you have a cylindrical electron collection grid. Okay, so you have a collector which is grounded, a filament which will emit the electrons, and then a grid. Okay. So what you have here is the electrons now emit. The electrons are now emitted. They try to bombard with the gas molecules and produce ions, and positive ions will get accelerated towards the cathode. The negative ions will get accelerated towards the anode or towards the collector. Okay. Now the electron current, whatever current that it is measuring, is directly measures the pressure in the is an indication of the pressure system. The operating range is from about 10⁻⁻2 torr to about 1 into 10⁻⁻10 torr, which is quite accurate. So ion gauges are useful for measurement of very high vacuum levels. I will now discuss with you what is called a residual gas analyzer. What is a residual gas analyzer? Now you have a vacuum system, you evacuate, and then what is the gas that is present in the system remaining? What is the remaining content of the gas? after evacuation. What is it present? That is given by a residual gas analyzer. What does it contain? It contains an ion source, a filament which emits electrons. These electrons ionizes the gas molecules that are present. Now, the gas molecules which are present are now filtered according to the mass to the charge ratio by what is called a quadrupole mass filter. Okay. This quadrupole mass filter contains 4 rods. Okay. And 2 opposite rods are supplied positive and negative RF voltages. And the number of the molecules which are moving through the center core, they enter a collector. As we keep on varying the RF voltages, then the selective mass ratio of the ions are entering, the crossing through this quadrupole mass filter and gets collected at the collector. Okay. So essentially it produces a mass to charge spectrum like this. So you have a spectrum with the mass number, charge ratio. So for example, nitrogen M by Z 14, oxygen M by Z 16, then fraction of M by Z 17, water molecules of M by Z 18, etc. The nitrogen or carbon monoxide, oxygen again M by Z 32, argon M by Z 40, and then carbon dioxide M by Z 44, etc. are just seen as a spectrum. So what is the vertical is indication of the intensity or the quantity. It is an indication of intensity. It is nothing but the amount, magnitude, quantity that is present. And the less height means lower intensity or lower magnitude or lower quantity present. So this is what is called an RGA spectrum. Now the RGA spectrum, as you can see, the relative intensity as a function of the mass number by Z. So hydrogen, water, nitrogen, oxygen, carbon dioxide, etc. can be seen. So it is for a system with air leak is the type of spectrum what you get. Suppose the RGA, you just sit on a particular ion of, let's say, nitrogen or oxygen, then if the relative intensity, if there is a leakage in the system, you will see that the peak will go to higher values, indicating the system is having a leak. Okay. Now, when we come to leaks, how do we detect leaks in a vacuum system? That's what we are going to talk about. I will skip this particular part. We will probably discuss this at a later time. Okay. I will discuss all this at a later time. We will only discuss the leak detection part. When you put a material inside a vacuum, then as I mentioned already, the material will give out all the gas molecules. That is what is called outgassing of the material. The outgassing of the material can be a limiting factor to achieve a good vacuum. Usually, it is best to use stainless steel, aluminum, glass, copper, etc. It is best to use this. And if you are using elastomer gaskets, O-rings, etc., if you are using that, they have to be manufactured specifically for vacuum applications. Then only they will be able to be good for vacuum applications. Please do not use brass, zinc, other alloys, etc. for vacuum applications. If you are using, you have to initially make sure that they are properly heated and then degassed, etc. Right. So outgassing is the spontaneous release of gas molecules from the solid surface or a liquid, in particular release of gases from a surface to atmosphere. What is degassing? Degassing is the deliberate removal of gas molecules. How do we do this degassing? You normally evacuate or you heat. Then both the cases, gas molecules with the adheres to the surface will come out. What are the normal leaks that happen in a vacuum system? Now, this refers to the leaks that are occurring in a vacuum system. So you can think of different type of leaks. The word leak can refer to the following. For example, you can think of a backstreaming. For example, oil vapor molecules can come back into the vacuum system. That's what you call backstreaming. Outgassing refers to the surface actually having certain amount of molecules of other gases. Okay, and that gas molecules can keep on coming into the vacuum system. As the vacuum here improves, these molecules keep on coming. This is what you call outgassing. What about diffusion? Diffusion again belongs to the same phenomenon where the gas molecules can come inside by diffusion. Permeation is the process through which a gas from gas from outside can permeate through the material and enter into the vacuum system. That is called permeation. There are real leaks, which means there are holes through which gas molecule from outside can enter into the system. These are called real leaks. And there are something called virtual leaks, in which there is a crevice, or let's say there's a dent in the vacuum system, in the pipeline or something. So gas molecules are all trapped inside. And as you evacuate here, then the gas molecules keep on coming in. So all this put together, it is called leaks. Okay. They are known as leaks in the vacuum system. Okay. Now, of these, the real leaks and the virtual leaks have to be seriously considered. You have to consider these two very important. Both the real leaks and virtual leaks have to be considered, because the others can be controlled by heating, etc. Whereas the real leaks, you certainly cannot control unless it is plugged. So also virtual leaks, it will keep on coming until it is probably closed. Okay. As you can see, leaks is something which is very important to close. If you do not close this, you will never be able to keep your vacuum system ongoing. So this is a cartoon to show you that there is a need for taking care of leaks. Okay, leak rates, for example, if it is 10⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻ seconds. On the other hand, if you have a leak rate of 10 raised to minus 9 standard cc per second, you get 1 cc of gas in about 30 years. So that sort of leak rates are there. So how do we detect the leak? You use what is called a leak detector. So for the leak detector, this is a test piece. It has to be evacuated and by using a suitable pumping system. And then you have what is called a mass spectrometer leak detector, which is connected to this. And using the mass spectrometer leak detector, you can evacuate the spectrometer tube. The mass spectrometer leak detector will be able to detect the leaks on the system. The gas molecules will be trapped here, and then it will be able to find out the leak. Okay, how does a mass spectrometer leak detector work? So mass spectrometer leak detector is normally tuned for helium gas. So now there is an ion source, okay, and the gas from the outside from your vacuum system is ionized, and then and it is now entering inside the mass spectrometer zone, and it is now coming as ions. These ions are entering, and you have a magnetic field applied, and the magnetic field is such that it deflects all the ions other than helium. Only helium ions are deflected 90 degrees and enters into this chamber, into the collector, and then it goes to the preamplifier, and thereafter the regular amplifier to indicate a signal. Okay. Now let's look at the leak detection. Suppose this is the chamber or a test piece which you want to test. Suppose let it be having a leak here. All that you do is this chamber is evacuated and it is connected to the mass spectrometer leak detector system. So this is the leak system. It is sensitive helium gas. Now you use the helium gas from a cylinder then spray the helium gas on the top of this. So if there is a leak, the helium will enter into this zone and goes to the mass spectrometer. Now helium ions are seen. Now this helium ions now produce a signal, both in the analog indication or a digital indication, and you also see a acoustic indication is seen. So you see a sound signal, the sound signal indicating that there is a leak in the system. So by spraying the gas at different parts of your component, you will be able to identify the leak. If the leak is there, the system has to be redone or re-welded. Then only the leak can be closed. Okay. Okay. There are a large number of applications of vacuum technology. I will do this particular part again in another class, maybe the next class on Wednesday. I will do it once more, but I'll just briefly tell you it has applications like common applications of holding objects, etc., or vacuum cleaner at home, what you normally use. And then it has an application for semiconductor industry, for processing of semiconductor devices and so on. Then you can create thin film developments by sputtering. Then we have some development done at IISc. This I will skip for the time being. We'll discuss again. We developed zirconium nitride based sensors using sputtering process. It is useful for vacuum in food industry, food packaging, for example. Vacuum packaging is possible, food drying is possible. And then in cryogenics, you require vacuum technology because as you can see, the heat transfer is considerably reduced by vacuum techniques, by using vacuum. So there are cryostats, storage vessel, any cryogenic system requires vacuum. For example, cryopumps are used for various applications like fusion, accelerator, etc. Vacuum technology is an important application, is an important application field, and as many developments have taken place over the years. And cryogenics and vacuum technology are twin fields, and each need the other. And several future developments have taken place in both the areas. And cryogenics requires certainly vacuum technology, and also vacuum technology requires cryogenics. Okay, and I thank you for your patient listening.